All right, we are recording, and what we're doing now today, these differential equations, you have learned about differential equations, and now with section 7.3, you learn that if a differential equation is separable, you can sometimes solve the differential equation and get an explicit solution. And actually, the homework problems you have, you can get explicit solutions for those differential equations. And now what we want to do is, now that we're familiar with differential equations, we want to do some applied problems. So let me give you a moment to copy this example down, and then we'll discuss the how to solve it. Okay. All right, let me give you a few moments here to copy this example down in your notes.
Professor, did you call this never mind. You called this separable equation, that's differential, right?
7.3 is separable equations.
Okay,
That's
thank you.
that's right. That's right, Jonathan. Yep. Okay, so let's take a look at this problem. It's an applied problem. We have a tank. We have a tank that contains, and I'll maybe start writing a little bit here. We have a tank that contains 20 kilograms of salt dissolved in 5,000 liters of water. And what happens is a briny solution that contains 0.03 kilograms of salt per liter enters the tank at a rate of 25 liters per minute. Okay. The solution is kept thoroughly mixed and drains from the tank at the same rate. It drains from the tank at the same rate. So let me ask you this. First of all, why do we need to drain the tank at a rate of 25 liters per minute? We have a briny solution entering the tank at 25 liters per minute, but then we are going to drain the tank at the same rate. Why do we Why do we do that? Why can't we drain the tank, for instance, at a slower rate? What would happen if we drained it? Well, I'm not looking for actually a pressure argument, Jonathan, but I know you're on sort of the right track. Why couldn't we drain the tank at a slower rate than 25 liters per minute? What would happen to the solution? Well, and Clay and Suzanne, I'm getting answers there. It's not quite the answer I'm looking for though. If water enters the tank at 25 liters per minute, and then we empty the tank at 10 liters per minute, what's going to happen eventually? What's going to happen eventually to the solution in the tank? What's going to happen to it? If we drain the tank at a slower rate than the rate of the solution coming into the tank, what would happen eventually to the solution in the tank? Well, getting all kinds of interesting answers here. Let me tell you what. Let me give you a hint. An 8-letter word. O-V-E-R. Overflow. That's right, Dion. Yeah, I mean, you know, if the brine's coming in, if the brine's flowing into the tank at a rate of 25 liters per minute, and we were to drain the tank at a slower rate, 10 liters per minute, eventually there would be overflow in the tank. So you can't have that. Now you can have the tank draining out at a faster rate than coming in, but you can't go the other way. So I'm just saying, you know, it's kind of just trying to get you to think about this problem. And they're asking how much salt. Okay, so how much salt remains in the tank after half an hour? So what makes this word problem different than the problems that you did from 7.3? The problems we looked at that you did in your homework, and that that we looked at so far in chapter 7. What's missing from this problem? What do we need to find for this problem? What do we need to solve? The rate. Okay, Susanna. And well, and so we need to find, what do we want to model this situation with? This application. What do we want to model it with? What kind of equation are we going to model this situation with? Well, not an integral, Clea, but how about a, you know what I'm looking for? I'll give you a big hint. Differential equation. That's right. That's right, Clea. Yeah, we need a differential equation to model this problem, to model what's going on here. So first of all, what we have to do is we have to define a variable. And this may be unlike anything you've ever done before, but that's okay. You're getting in higher level, you're in higher level math now. And you know, we got to see, you know, we got to try to do some applications. So what I'm going to do is I'm going to let y of t equal the amount of salt and the units are going to be in kilograms in the tank after t minutes. And actually, I have this on the next page. Let me go to the next page here for the solution. So, okay, so this is our solution. So we're letting y of t be the amount of salt in kilograms. Okay, and I should say in the tank after t minutes. I mean, differential equations have dependent variables and independent variables. The y is your dependent variable. The time t is your independent variable. We want to find a differential equation for dy dt. And for a tank problem, the dy dt, the differential equation, would be based on the rate of salt coming in minus the rate that salt goes out. Okay, so we need to find an expression for y of t. We need to find a formula for the amount of salt in the tank after t minutes. Well, in order to find the formula, we need to find the differential equation that models the salt rate in the tank. And keep in mind also that for dy dt, the units are in kilograms per minute, because salt is in kilograms, that's the y, and time t is in minutes. So, you know, you have essentially salt coming in at a certain rate in the tank because of the briny solution entering the tank. And then, you know, at the same time, the tanks being, you know, stirred or mixed. And when you drain the tank, you have salt that leaves the tank also. So rate in minus rate out would be the model for this differential equation. Now, what would the rate in be? Well, the brine solution, okay, let me just, yeah, the briny solution, the brine enters at 25 liters per minute, okay? But the concentration of the salt in the briny solution is 0.03 kilograms per minute. And notice what happens here to the liters. They cancel out, leaving you with kilograms per minute. So the rate of salt flowing into the tank is 0.75 kilograms per minute. So you see how you can use the units to help assess that you're doing the problem right. Like in chemistry, how many recall in chemistry you use units to help you? Sure, Masumei knows that. And let me see here. Hold on. And sorry, I'm just looking here. Right, right. So that's your rate in. Now the rate of salt going out of the tank. Jonathan, I'm not sure, but I know in chemistry, when I took that class a number of years ago, it helped me a lot to put the units in my computations, and that way it was a double check that I was doing things right. And for the rate out, well, the rate out, okay, Clea and Jonathan says stoichiometry. Okay, so that's a branch of science dealing with the units. That's good. That's good. And so now rate out. Well, the solution flows out at 25 liters per minute, and the concentration of salt in the solution is equal to the amount of salt in the tank, which is your Y of T, okay, and divided by 5,000 liters, because there's 5,000 liters of water in the tank. Well, the tank contains 5,000 liters. It's not going to be, it's not pure water because you have 20 grams of salt that dissolve in the water. But the point is the tank holds 5,000 liters. So this means then the rate out is Y kilograms per 200 minutes. If we, if we take 25 here, if we take 25 and divide it into 5,000, 25 goes from 5,200 times. Okay, so this means then that dy dt would equal 0.75 minus y divided by 200. Rate in minus rate out. Are there any questions on that so far before we move forward? Yes, Jonathan.
What it says in the beginning of the problem that we know how much salt is in there. It says 20 kilograms of salt is dissolved in 5,000 liters of water. Why is there Y of T instead of just 20 kilograms?
Well, indeed, we know initially there's 20 kilograms of salt in that tank, but the salt content's changing because if we very good question. There's brine, a briny solution, that's a salty solution that's entering the tank, and that's going to change the amount of salt, the salt content in the tank. Okay, good. Okay. Are there any other good questions before we move forward? All right, well now we have a differential equation here to solve. Okay, so let's proceed on and try to solve this differential equation. Clea, the tank, well, the tank and the brine are two separate things, absolutely. The brine enters the tank, and then it's mixed up into the tank, and then the solution leaves the tank at the same rate. So the tank just maintains, there's always 5,000 liters in the tank, but the concentration of salt in the tank is going to change over time. Okay, all right, well then let's see here. All right, so here's our differential equation. And what I want to do, what we want to do here, okay, is, there's the differential equation, but I'm the only technique I've learned to solve a differential equation is separation of variables. So what we're going to do is we're going to rewrite I mean, this here, if I have a 200 denominator here under the y, why don't I get a 200 denominator under the 0.75? So I'll multiply 0.75 by 200 over 200, and then that'll get me 150 over 200 minus y over 200. And so this will get me 150 minus y divided by 200. Now we can separate the variables. Okay, so we're down to here. Let me give you a moment to catch up, see if there are any questions.
Professor, can we do this without the step that we also give the numerator to 2.75? Can we do without that?
Sorry, Clea, say again.
Can we solve the equation without giving the denominator also to 7.75?
I don't think so. I don't think so. I think you need to, good question. In order to separate the variables, we need to have the differential equation be in a format like this where we can separate the variables. So I'm trying to think if there was some way. Yeah, I think we have to get it in this form, Clea. And so if you notice here, okay, if you notice, we have it in the form. And what we can do now, if we want the y term on the left, y variables on the left, and t variables on the right, we can multiply by dt both sides. And if we do that, then we're going to get dy equals 150 minus y over 200 dt. But then what we can do here is we can then multiply both sides by 150 minus y. 150 minus y. I'm sorry, 1 divided by 150 minus y. That's what I want to do. Hold on, the new format, my pen's a little bit bigger, so I gotta be a little careful how I write stuff in here, but 1 divided by 150 minus y. And so what happens is the 150 minus y's simplify out, and then this is going to get us right there. See that? Try to separate things a little bit here. Do you see, Clea, how helpful that was? And I don't know how you would separate it if you didn't do that step. Are there any questions on that? Does it help my putting how many find it helpful just marking with the pen certain things? Is this helpful? This sort of, okay, Yonatan's liking that. All right, good. Colors show relation. I agree with that, Yonatan. Well, all right, so here we are. Now we have a separable differential equation. And we're going to integrate both sides of the differential equation. So when you're ready, I'll go to the next page. If there are no questions, and we'll continue. Victoria says, why didn't you just multiply the 200 first? I could have done that. Well, I just wanted to, I mean, I could have it like this, you know, like for instance, I could have done this. I could have had 200 over 150 minus y dy equals the integral of 1 dt. That would also be acceptable. But I just kind of like it the way I have it up there. All right, Victoria? Is that so far so good? Okay, you're welcome. Are there any other questions? All right, well then let's proceed on here. Let's proceed on. So here's the differential equation. And on the left side, I'm going to do a substitution. If I'll factor the 1/200th out on the right side. And then I'm going to do a substitution here on the left side. I'm going to let u equal 150 minus y. Then du is negative dy, so negative du is dy. And so the left-hand integral I can write as the left-hand integral as the integral of 1 over u negative du. And the antiderivative of 1 over u is the log of the absolute value of u. So negative times the log of the absolute value of u will equal then, now like here, incidentally, over here, the integral of 1 dt is just t. And of course, we have constants of integration. We can combine them and just put a c1 on the right side. So now we took a differential equation. We did integration by part. We separated the variables, and now we're gonna solve, eventually find a solution for the amount of salt in the tank at time t. So what I'm going to do now is I want to get the u, or absolute value of u, alone. So I'm going to multiply by -1 on both sides of the equation, and that's going to give me the log of the absolute value of u equals negative t over 200 minus c1. But minus c1 I'll call just plus c2. And then here we are again. We want to find out what the absolute value of u equals, so I'm going to exponentiate both sides of the equation. Yes, Clea?
Why do we call C1 C2 again?
Well, what you have here is you have a negative C1. I'm just choosing to call that C2, but I could have had negative C1. In other words, if you had the log of the absolute value of u equals negative t over 200 minus C1, that would be okay. That would be okay. I just find it easier to replace I just like to have positives that I want to be careful. I'm not saying plus C2 is a positive value, but I just like to reduce the amount of negatives I see in the equation. Okay, and then of course over here, maybe I'll put this in red. over here, right? This just equals E. Well, I mean, what I'm trying to say is if you have E to the A plus B power, that equals E to the A times E to the B. And that's what I use to get down here. Going from here to there. E to the C2 power, okay, E to the C2 power, I'm going to call that C3. Just because it's easier for me to rename the constant. Sorry about that. Sorry about that. Let me go back here. Hold on. So, hold on here. So, you know, my gosh, hold on. Hold on. All right. So, we were here. Okay. So let me go back here. Thank you, Clea. Thank you, Jonathan. Everybody, I assume everybody's good. Everybody's good up to here, right? Keep in mind, we're looking for Y of T, which is the amount of salt in the tank at time T. We know we're going to have to put back in what U was. U was 150 minus Y. We're going to have to put that back in here because we want to solve for Y. So if I go to the next page, that's what I do. Okay, I go ahead and put back in the 150 minus Y for U. And 150 minus Y, again, you know, remember, if you have, I'm going to say it's the right way. If you have the absolute value of an apple equals a pear, then the apple equals plus or minus the pear. So it's the same kind of thinking here. We don't want these absolute values to be here. We'll remove them, so we get 150 minus Y, but that means then we introduce a plus or minus over here. But the plus or minus C3 times E to the negative T over 200 can be thought of as plus or minus C3 times e to the negative t over 200 power. And we can replace the plus or minus C3 with C, which is what I do here. Now that's just sort of, that's a way to always handle when you have an absolute value, how to handle it. I'll note here that it turns out that 150 minus y will always be positive. So, you know, we could have just, well, I mean, I don't want to, let's not get too technical here. Let's just proceed on. We have an approach that works and we're fine. So, okay. So we can solve for y. There you go, then. If 150 minus y equals this unknown constant times e to the negative t over 200, this means then, and notice I'm calling now I'm putting a c in there. I'm not like calling this constant C4, although I could, but I'd put it in there because I know it's like the last time I'm going to have to alter a constant. But now y is equal to 150 minus c to the power e to the negative t over 200. And that's great. We've solved for y. But we still have this unknown constant c. The formula is no good to us unless we can figure out what that constant c is. I mean, we basically here have a family of solutions, right? Because that constant c could be, it could be anything. However, if we specify this initial condition, okay, y of 0 equals 20, and where are we getting that from, by the way? This initial condition.
Isn't it from the problem that a tank contains 20 kilograms of salt?
That's exactly right. That's exactly right, Clea. Very good. That's right, Jonathan. The start of the problem said, when you copied the problem down, it said a tank contains 20 kilograms of salt dissolved in the water. So that means at time 0, right before you have the brine entering in the tank, you have 20 kilograms of salt in the tank at time 0. So y of 0 equals 20, and we'll put in then the initial condition t equals 0 here. So e to the negative 0 power is just 1. And so we can solve for the constant. And so it turns out the constant of integration, or no, not integration, just this constant will equal 130. And so now here is the formula that we've been wanting to find. And on your next exam, naturally, I'm going to be looking for this work. If you have an exam problem like this. Now, based on the differential equation, we have an expression for y of t, a formula that tells us the amount of salt in the tank after t minutes. So how are we going to find out the amount of salt in the tank after 30 minutes? What do we do with the 30 minutes? T equals 30. That's right, Jonathan. And incidentally, that's right. We'll substitute t equals 30 in the equation here, and we'll solve. Now, if for instance they said, tell us the amount of salt in the tank after like an hour, what would you have to do if they said find the amount of salt in the tank after an hour? That's right. You'd have to convert the hour into minutes because our units are minutes. The dt, the units were kilograms per minute. All right, so you just have to be conscious of that. Here we go. Okay, so after 30 minutes, the amount of salt in the tank will be approximately 38.1 kilograms. Let me give you a moment to copy that down. So after 30 minutes, the amount of salt in the tank is no longer 20 kilograms. It's grown to 38.1 kilograms. So that that's okay. It makes sense. We're pumping in this briny solution into the tank. And even though we mix the tank and empty the solution, we're still pumping in this salty solution. So it's going to make the tank saltier over time. And notice as t goes to infinity, well, what's the limit of the amount of salt in the tank as t goes to infinity? Well, e to the negative t over 200. Let me see here. Maybe I can put in just an additional step here. So this is going to equal 150 minus 130 times e to the negative infinity. Okay, but let me see here. Let me do it again here. Sorry, class. Let me do this again. One moment. So this is going to be 150 minus 130 times e to the negative infinity, over 200. But if you think about e to the negative infinity divided by 200, that equals 1 over e to the positive infinity divided by 200. And what's that going to equal? I mean, what is this go to?
0?
Yeah, that has to go to 0. That's right. Good, Claire. Good, Jonathan. That goes to 0. So this leaves us with 150 kilograms. And this makes absolute sense because over time, we have that the concentration in the tank approaches, the concentration of salt in the tank approaches 0.03 kilograms per liter. Even the 20 kilograms of salt initially in the tank is irrelevant. What matters is what's happening over time. So hold on, let me make this in blue. What matters is what's happening over time. So over time, the concentration of salt in the tank is 0.03 kilograms per liter, because that's what the briny solution is. Okay, and so if you take 5,000 liters, that's how big the tank is, and multiply it by 0.03 kilograms per liter, you get 150 kilograms of salt. Okay, it's I don't know, I think of it like how many have had I mean, I don't know if it's a good analogy, but I'll just how many like a chocolate shake? How many have had like a chocolate shake before? I assume it's everybody, but all right, Masume has. And you know, in the beginning when you drink the chocolate shake, it's a little chocolatey, right? It's a little chocolatey, but to really get the full effect of the chocolate, don't you have to suck up the suck the chocolate shake for a little while? How many kind of notice that? In the beginning, maybe it's a little chocolatey, but over time, then it's like kind of stays constant, the chocolate feeling that you have in your mouth. How many have noticed that? Okay, Masume knows that, and so it's the same kind of thing. It it doesn't really, and I'm just trying to think of sort of an analogy that maybe students that you're sort of familiar with. The point is that over time, because you're pumping in this briny solution in the tank continuously, and the concentration of salt is 0.03 kilograms per liter, eventually the tank is going to take on that characteristic, and the concentration of salt in the tank will be 0.03 kilograms per liter. The fact that you had 20 kilograms of salt initially in the tank doesn't affect the actual end result in terms of the concentration of salt in the tank. Now, it might help it to get to that concentration more quickly, but it's the same. It's not. What's the word I'm looking for? It's not. It doesn't affect the end behavior. And actually, if I bring up the ebook here, this is actually example 6, the example I did here. I want to bring up the ebook for this problem. Let me just find it here. One moment, I have it, but we're in section 7.3. All right, hang on. Let me go into the book here. So we did what's called a mixing problem, and they're very common. You'll see them in differential equations, math 282 as well. And we did example 6 here. We did example 6, and this is a picture. This is a picture of the function y of t. So y of t was equal to, actually, if I want to just go back to the, one moment. I want to go back to the solution here. It's worth doing it. So here's the solution, the amount of salt in the tank at time t. At t equals 0, at t equals 0, what's y of 0 going to equal? That's right. Good, 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 Jonathan. Because if at y, when at time 0, we would have 150 minus 130 times e to the negative 0 over 200 power, but that's 150 minus 130 times e to the 0 power, but e to the 0 power is just 1. And so 150 minus 130 times 1 is 20. And that absolutely makes sense. I mean, you start off with 20 kilograms of salt in the tank. So when we go, what I'm mentioning this because I want you to be comfortable with the picture that they're showing. Okay, so there's the graph in figure 10 of that, of y of t, which is equal to 150 minus 130 times e to the power negative t over 200. You see there in figure 10 how it starts at 20, the purple graph, and then it moves up to what? It moves up to 150, and then it starts to level off over time. That's because the concentration or the amount of salt in the tank will never be more than 150 kilograms. So that's like it's reached what's called a carrying capacity, so to speak. Are there any questions on that? Okay. I want to look at something else in section 7.3 before we go on break here. I want to look at another type of problem that is important. It's called orthogonal trajectories. Orthogonal trajectories. So, an orthogonal trajectory. This is in the book, in the ebook, section 7.3. Orthogonal trajectory is a family of curves that intersects each curve of another family at right angles. At right angles. Okay, so like for example, they give here in figure 7 and 8, they give nice pictures for you. So you see in figure 7, they have these blue curves, and there's a purple orthogonal trajectory that intersects those curves at right angles. And in figure 8, what they have two sets of orthogonal trajectories. Okay, you have two sets. You have a family of circles, okay, concentric circles, and that family of circles is orthogonal to the family of straight lines. You see that? So each straight line through the origin is an orthogonal trajectory of the family of concentric circles. That's what they're showing in figure 8. And these are important. These are important, for instance, I want to say, so I actually Googled this just so I can tell you it very nicely. Orthogonal trajectories are used in mathematics, and they appear in physics, such as electric fields and their equipotential curves. Has anybody seen that maybe in physics? Electric fields and equipotential curves. All right. Well, okay, Franklin has. Okay. So Franklin, does this sort of, this orthogonal trajectory, does it ring true to you with what you've seen?
Yes, professor.
Good. Excellent. 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 So, okay. Let's look at an example here. Excellent. Thank you. Let's look at an example here. Example 5. They say, in this example, find the orthogonal trajectories. Find the orthogonal trajectories of a family of curves where x equals k times y squared, where k is an arbitrary constant. So x equals k times y squared. That's a family of parabolas that open sideways. Okay, that's a family of parabolas that open sideways. They're not up and down parabolas, they're sideways parabolas. And we want to find the orthogonal trajectories to those parabolas. So like for instance, I think it would be good to see a picture of this. This is like what we're talking about here in figure 9. So in figure 9, you have the blue parabolas, which are in the family x equals k times y squared. As k changes, the parabola, will grow more quickly, so to speak. And it appears, looking at that the orthogonal trajectories are the purple graphs appear to be what? So the blue graphs in figure 9 are the parabolas. And that's right, Jonathan. The purple graphs appear to be ellipses. So it appears that orthogonal trajectories to this to these set of parabolas appear to be ellipses. But there are all kinds of ellipses. We need to know more specific information about the ellipses. So how are we going to do that? Well, here's what we're going to do. Here's what we're going to do. So x equals ky squared, k times y squared. We're going to differentiate. So I'll tell you what. Let me go. Again, this is example 5 that we're looking at. But let me kind of switch back and forth between the book and the whiteboard, so I can help guide you a little bit on this. So, okay. X equals k times y squared. We're going to differentiate both sides of this equation. So these are my family of parabolas. And I'm looking for the orthogonal trajectories. And this is, again, example 5 in section 7.3. So what we'll do is we'll differentiate both sides of the equation. And this is how you would do all of these kind of problems. You'll have several you'll see in your homework. Yes, Claire? Yeah.
Why is it d over dx for the ky? Isn't it supposed to be d over dy?
Well, what you have, that's a good question. What you have here is you have this family of parabolas, and you're going to differentiate the equation. So if you differentiate the left side with respect to x, you have to differentiate the right side with respect to x. Okay, so we could differentiate both sides with respect to y, for instance, but we want to do it with respect to x. And watch what happens here. So the left side is going to become 1, and the right side, well, a constant, I can bring a constant out in front of the derivative. And so 1 will equal k. Now what's the derivative of y squared. That's going to be 2y times dy dx. Okay, what did I use there? What did I use there? What did I do here to get this? Think back in Calculus 1. What type of differentiation is this? Begins with an I. IMP. That's right. Good, Yonatan. Implicit differentiation. That's what we did here. So it's been a while since you've seen that, but here it comes back. Okay, so now I'm going to tell you why we're doing this. So, why are we doing this? I'll show you why in just a moment. So we have then that 1 equals 2ky times dy dx. And this means then that dy dx equals 1 divided by 2ky. So for my family of parabolas, the derivative of y with respect is equal to 1 over 2 times k times y. But I can replace the k. By virtue of the fact that x equals k times y squared. I can replace the k with x over y squared, because k equals x over y squared by virtue of that equation there. And so when we do this, okay, we can simplify this. We can simplify this as 1 divided by 2 times x over y, and that equals 1 divided by 2 times y over x. And so that's y divided by 2x. So all the parabolas, okay, I want to say this the right way. All the parabolas, the derivative of y with respect to x is equal to y divided by 2 over x, and we're going to make use of that. This is, remember what this is. This is a slope. Now, if you're looking for orthogonal trajectories, and I'll be right there. I know there are a few questions. If you're looking for orthogonal trajectories, and I'm sorry, I'm just I'm a little limited on my space, but we're okay. Orthogonal trajectories. Thank you, Clea. Thank you. Okay, Mandy's question's answered. What would their slopes be? What would their slopes be for orthogonal trajectories? If the slope for at any point xy, if the slope for the family of parabolas, the slope of a tangent line at any point on the family of parabolas is equal to y divided by 2x. Orthogonal trajectories, which are perpendicular to the parabolas, what slopes would they have to have? You
Um,
have
1 over, I think, y over 2x.
good. -1. That's right, Claire. -1 divided by y over 2x. So the orthogonal trajectories would have to have slopes of -1 divided by y over 2x. And actually, I have enough room here on the corner to do this. If I just sort of bring an arrow here, if the slope is -1 divided by y divided by 2x, that's just going to equal then, that's just going to equal -2x divided by y. -2x divided by y. And that's what they're saying in the book. So if we, and this is all in the recording, but if we go back to the book, here, then they're saying that since the slope of any tangent line on one of the parabolas is y divided by 2x, let me make that a little bigger. Since the slope of the tangent line at any point on one of the parabolas is y divided by 2x, an orthogonal trajectory of the tangent line must be the negative reciprocal of this slope. So that's a fact that you learned probably back in pre-calculus or earlier, right? Two perpendicular lines, their slopes are negative reciprocals of each other. How many recall that? Maybe in algebra 2. Okay, Clea recalls it. Anybody else? I hope more people recall it. Two perpendicular lines, their slopes are negative reciprocals. That's right. That's right. So that means then for our orthogonal trajectories, dy dx has to equal -2x divided by y. Okay. And let me just see here. Let me go back to the whiteboard real quick. Yep, and that's what we showed, you know, here. There's -2x over y. So that being said, let's finish the problem up. So we said that based on the picture here in figure 9, I don't know why that's showing. I don't want that to show. Let's get that off there. In figure 9, the orthogonal trajectories to the parabolas look like ellipses, and let's verify that. So what we can do is we can take the slopes for the orthogonal trajectories, which behave according to the differential equation dy dx equals -2x over y. We can separate the variables. And when we separate the variables, we end up getting, let me just see it. I don't particularly like, let me see if I can highlight it. That's fine. When we move this up just a tad. So when we separate the variables of that differential equation in pink there, we'll get then that x squared plus y squared over 2 equals a constant. Well, that x squared plus y squared over 2 equals a constant. That's just in the form of an equation of an ellipse. Okay, where the major axis, under the x squared you have a 1, under the y squared you have a 2. So since the number under the y squared is the 2 is greater than the 1 under the x squared, that means that the ellipses have to be longer in the y direction, if you remember ellipses. And so here you go. Yonatan, yes.
Where did you get negative 2x over y from? I understand how you got from the beginning to y over 2x, but I'm not sure where negative 2x over y came from.
Okay, hang on. Let me go back to the whiteboard. Let me go back to the whiteboard. One moment. Okay, hold on. Let me clear this, or let me see here. What's this? No, we're good. Okay. Yep, hold on. Let me clear that. Okay, so for the, let me see here, for the parabolas, okay, and there's a little background noise here. That's not me. That's somebody else just in the room. Don't worry. You have that you have this is your dy dx, y over 2x. And then you have your orthogonal trajectories. Now, the y over 2x is a slope. We're looking for the slope of the orthogonal trajectories such that the product will equal -1. Well, the only thing that would work would be -2x over y. And so for the orthogonal trajectories, dy dx equals -2x over y. It's just like, when you have perpendicular lines, the product of their slopes, m1 times m2, has to equal -1. That's a very common thing that hopefully you've seen in your in algebra or somewhere along the way. But it's, in fact, it's the truth. It's the truth. It's like if you have a line where the slope is equal. All right, excellent. The slope equals a half. Well, the perpendicular line would have the slope equal to -2 over 1. If one of the lines, it has a positive slope, it's going upward. The perpendicular line has to have a negative slope. It has to go downward. It's perpendicular, and the slope's -2 over 1. Okay, Yonatan's good. Excellent, excellent. Are there any other good questions there? Okay, well then, so now hopefully we're comfortable with this problem, and I think we'll go on our break here. But are there any questions? Everybody's good? Maybe give me a thumbs up if you're comfortable. I mean, at least reasonably comfortable. with what you're learning here. Okay, clay is good. Might we have a few other people who are, I know you got to practice. I know. Um, okay, all right, I'll stop the recording then. Maybe give me just, can I get maybe just one more thumbs up? Maybe just somebody else who's at least a little bit comfortable. Okay, thank you. Thank you. I forget, somebody did that real quick. Oh, thank you, Jonathan. All right, I appreciate it. Okay, let me stop the recording.